You hear that? It's coming. Don't. It's knowledge. It's coming for you. So today we finally get to start talking about inferential statistics. That's statistics where we work to infer information about a population. So whether we want to know the population's mean or the population's parameter, we want to use statistics to make a guess about what that value actually is. And so as we work through this, we need to keep track of when we're talking about a population and when we're talking about a sample. So whenever we're talking about the value of a population, that means that we're trying to talk about the parameter of a population. So if we're trying to talk about the population mean, we use a mu to represent that. If we want to talk about the population proportion, we use a p to represent that. And if we want to talk about the standard deviation of a population, we'll use sigma. Now, on the other hand, once we take a sample from that population, the values that we get from that data are called statistics. And so for a sample mean, we'll use x bar. For a sample proportion, we'll use p hat. And for a sample standard deviation, we will use S. And so mu, p, and sigma are going to be parameters because they're talking about a property of the population, whereas S, p hat, or x bar are going to be statistics because they talk about properties of a sample. So say you're interested in renting an apartment and you want to know what the average cost of an apartment in Owensboro is. So you get online and you sample some ads for apartments or look at different websites and you pull some average rents for the apartments that you're looking for and you calculate their mean. That mean that you calculated is going to be a statistic. So the mean rent for a sample of apartments is going to be x bar. And the goal of doing this is to try to use the information that you have about x bar from your sample to figure out what you think the actual mean price of an apartment is. So you're trying to use x bar to infer some information about the parameter mu. And this x bar, this is what we call a point estimator. Meaning that it's a single point that based on the data that we have, this is our best guess for what mu is. Right? Because if we have no other information, we've just taken a sample of some apartment rents and we calculated this mean. That's all the information we have. That's our best guess. Now, if we've sampled correctly and we've pulled enough data, it's reasonable to think that even though x bar is probably not exactly equal to mu, it's probably pretty close. And so we can ask the question of, well, how close do we think it is? And that's where confidence intervals come in. All right, so what is a confidence interval? So in the previous example about apartment rent, right, we have the actual population mean, mu, for renting an apartment. So this is apartment costs in Owensboro. And we have a sample mean of X bar. So let's say that out of our sample, we came to an average rent each month for an apartment of $500. So let's say X bar is equal to $500. And let's say that we have some historical data that says that while the actual price of an apartment, the actual rent value, can go up and down depending on the market, the spread of the values in town has been pretty consistent. So let's say that we know that the standard deviation of apartment values in Owensboro is known to be have a standard deviation of $75. And let's say that the sample that we took to calculate our $500, let's say that we took 25 apartments. So our N is equal to 25. Now, we don't know the distribution of these rent values, but we have some information. We say we know the standard deviation, we know our sample size, and we know what sample mean that we got. And so what we want to do now is we want to construct what's called a 95% confidence interval. And what we mean by that is we said that X bar probably isn't equal to mu, the actual population mean, but it's probably close. So what we want to do is we want to construct an interval around X bar to where we're 95% sure that mu actually falls into that interval. So still, we don't know what mu is, but we're saying only 5% of the time are we expecting to get that the population parameter mu is going to be outside of this interval. And the way that we do that is we use the central limit theorem. So the central limit theorem says that the distribution of this X bar is approximately normal with a mean of mu and a standard deviation of sigma over the square root of n. And so what we're going to do is we're going to use our best guess for what mu is. And our best guess is the point estimator. It's X bar. And so we're going to consider a normal distribution centered at our calculated X bar with a standard deviation of sigma over the square root of n. So the standard deviation for X bar is going to be equal to the standard deviation here of 75 divided by the square root of our sample size, so the square root of 25, which is going to be 75 over 5, or 15. And so if you go back and remember when we talked about the normal distribution very early, we had the 99, 95, 68 rule, or the 68, 95, 99 rule, depending on how you learned it. And it says that we can pick up 95% of this probability between X bar minus 2 times the standard deviation and x bar plus 2 times the standard deviation. That if we look in here, that this is going to contain 95% of the probability. So that means 95% of the time we're going to get a value in between these two. And so looking at that, what that means is that if our standard deviation here is 15, that our 95% confidence interval is going to be our sample mean plus 2 times our standard deviation, and our sample mean minus 2 times our standard deviation. So for this particular example, our calculated standard deviation is $500. So this is x bar minus 2 times the standard deviation of x bar, which is going to be $500 minus 2 times $15, or $30. So this is going to be $470. And x bar plus 2 times the standard deviation of x bar is going to be $500 plus 2 times 15, or $530. So what that says is our 95% confidence interval is the interval from 470 to 530. And so what that means is we still don't know what the actual average cost of an apartment is, but we're 95% sure that the actual cost is somewhere between 470 and 530. And so while we still don't know the actual value of mu, this does give us some information. We can make decisions about the idea that we're reasonably confident that it's no bigger than 530 and no smaller than 470. So that gives us a place that we can work from. Now, there's other types of confidence intervals. We're going to talk about how we can construct different percentage confidence intervals. And we're also going to have to talk about the fact that it's probably kind of unusual that I would be able to know kind of what the standard deviation of the population is without knowing the actual mean. So we're also going to have to talk about how we get around the fact that we had to use some already known information. And what happens if we don't have that? Can we still make confidence intervals? The answer is yes, but it's going to require a slightly different approach.